Welcome, everyone. Thanks for coming to my talk. This is actually my first time at Devox and my first time at a conference in general. So I'm really excited to be here. Today, our talk will be about adaptable heap sizing for containerized Java applications. So while that might sound like a mouthful, I'll kind of go into what that means in a little bit. And the title, No More XMX, is a bit of clickbait. I wanted as many people to come to this talk as possible, so I made an outrageous claim. But of course, this is sort of also true. And so I'll sort of talk about what that means later as well. OK, so a little bit about me. Currently a senior software engineer on the Java platform team at Google in the United States. I live and work in the Bay Area, which is awesome. And I've been working on the Java platform team, and our role there is to make sure that Java is running smoothly and properly for all developers for Java at Google. Before that, I spent a couple of years working on distributed file systems at a startup called Rubrik in Palo Alto. So I'm a bit of an imposter here as well because I've written only C++ code my entire career. But I'm here at a Java conference talking about the JVM, which is what I've been working on. I also like to make some music on the side, so if any of you are all interested, I added my SoundCloud link sneakily as the third link below. So feel free to check that out and listen to some of the beats I've made. Also, feel free to send emails to me or connect with me on LinkedIn. I've provided my links here. And that's me drinking a non-Belgian beer, but I will say the beer here is amazing. OK, so the agenda for this talk, we'll briefly talk about the background of memory in containerized environments at Google, and then we'll go into some of the implementation details of adaptable heap sizing. We'll look into some of the benefits we've seen from using adaptable heap sizing within Google, look forward towards some benefits we want to expect in the future, and then finally, we'll, if we have time, have some Q&A at the end. And just for the sake of not running out of words to say, we'll be using the AHS to describe adaptable heap sizing for the remainder of this talk. OK, so who here runs Java in a containerized environment? OK, so most of you. I don't know what the rest of you are doing here then. No, I'm just kidding. OK, so for those of you raising your hands, who raised your hands, how many of you have had problems with running Java in a containerized environment related to memory, tuning XMX? OK, so a good amount of you, most of you actually. Great, so this talk will be very interesting to you, and hopefully it'll be interesting to everyone else as well. So let's look at what Java looks like, the Java memory model looks like in a containerized environment. So this is sort of a generic representation of what you can expect inside a container, but we have in green the Java memory, which is the XMX, which corresponds to the Java heap. And then the yellow part is the Java non-heap. So as part of a Java process, when you're allocating new objects, you allocate some on the heap. That is the green boxes. Everything else that's not related to the heap but still consumes RAM is the yellow box. And of course, keep in mind that for the XMX, which is the maximum size of the heap, your Java process won't necessarily always be using the full amount. That oftentimes the actual amount of RAM consumed is a subset of XMX. So that's why I have the light green box and the dark green box to differentiate the limit versus the actual usage. And then finally, in your container, you may or may not have other processes running which also consume RAM. At Google, we do, but I left it as a dotted line. That's the dark blue box. OK, so what we're looking at here is an optimal configuration where everything is running in harmony and we have a little bit of free space left in the container in case we have some fluctuations in memory. But of course, the total amount of memory being used by the various processes in the container are not often fully well understood. So obviously for the XMX, that is a hard limit. You will not have the Java heap use more than the XMX. But for the other processes, it might be hard to keep track of what is the right amount to have. So I sort of put question marks to denote that these are unknown values. And in the worst case scenario, if these unknown RAM consumers use too much, then we get in a scenario where, well, we have no more RAM left in the container. And that is what we call a container out of memory, container I'm sure you all are familiar with that already. OK, so how does tracking this look like? Well, at Google, we have ways to track the various RAM consumers inside a container. So looking kind of similar to the previous model, we have the XMX, which is the maximum Java heap. And then we have things like the metaspace, thread stack, malloc, code cache, Those are all RAM consumers part of the Java process, but unrelated to the heap. And then we have, without loss of generality, container process 1 and container process 2, which are simply the RAM consumers of the non-Java processes inside the container. So if we sum these all up, we have this green line. OK, so let's look at the red line first in the second graph. That corresponds to our container limit. So let's say in this scenario, we have a 2 GB container limit. And if we look at the sum of all the various RAM consumers, we might see that this exceeds the container limit. And this is risky because, as you know, you won't necessarily be using the full amount of XMX, but in any case, if in the worst possible scenario, the consumption of all the RAM of all the different processes exceeds the container limit, then we're at that scenario where we could have a container So you might be wondering, well, at Google, why is this such a common issue? Don't you have something to solve that already, given how big of a company you are? Well, not exactly, and I think understanding why requires delving a bit into the history of Google. So let's look at what's going on here. We recently made the migration from JDK 8, which uses the concurrent mark sweep garbage collector, to JDK 11, which uses the garbage first collector. And yes, we are behind, but it's pretty hard to stay up to date. And actually, we are working on things to keep the JDK closer to head, but that's a separate talk. OK, so what are the differences between G1 and CMS? Well, there's some things like heap regions are non-contiguous in G1. G1 tends to perform more compaction. But of course, G1 is also generally higher throughput, which is why they made the change to default. And at the cost of this, we tend to use more non-heap memory, as well as heap memory more greedily as part of G1. OK, so then why is this a problem? So let's look at that memory model that we created in the past and see how it applies to this scenario. So for CMS, a lot of the Java jobs running CMS, we had a configuration that was not really detected as being problematic because, as you can see, when you sum up all of the used RAM inside the container, there was still actually some container free space. And that's mostly in part due to the fact that the Java process was not using the majority of the RAM that it was given. However, these same services or same jobs, once we migrated to G1, we saw that because G1 tends to use heap more greedily, a lot of these started to have, of course, more RAM being used then by the Java heap, and then this caused it to go over the edge and caused a container So this is my attempt at a meme while following copyright restrictions. It would be funnier if I could use the real photo. I'm sorry. OK. Anyways, how do we address this then? Well, for the JDK 8 to 11 migration, we kind of used a Band-Aid approach because we were in a hurry and we didn't want to block adoption of JDK 11 on some big piece of technology that we had yet to implement. So what we did was we basically identified all the servers that were misconfigured in such a manner and simply reduced it using a formula. And the pros, like reduce the XMX, of these jobs using a formula. And so the pros of this approach are that it's, one, mostly automated, and two, it's just a one-size-fits-all approach. Basically, it's easy. But of course, easy is not correct. And so it came with a lot of cons. One, the memory limits become a lot less clear. Because we're changing the XMX from under people's noses, they might be saying, hey, how come my job is not configured with the amount of XMX that I configured it at? And similarly, there's a lot of unfixed edge cases that you'll see in just a moment. So this graph represents all of the misconfigured jobs. Each blue dot is a job that we said, hey, your maximum worst case RAM usage is higher than the container limit. And the vertical line is just like represents a 1-to-1 ratio of worst case memory usage and container limit. So everything above that line is problem. So then after we used our best fit formula to reduce the XMX of these jobs, we still had a lot remaining. So basically the ones that were close to that line, we were able to lower a little bit, but we couldn't drastically lower every single job by the right amount. It's just not tractable. So as you can see, there's still a lot of problems. And for the remainder of these jobs, we had to file bugs, reach out to the teams, work with them proactively to fix their configuration before they made the switch. So that was a lot of manual effort. Yeah, so not that great. OK, so another common problem that we noticed at Google is an anti-pattern which I like to call the memory cycle of doom. And it's very ominous sounding because it is ominous. Okay, so what happens is a server owner might observe a container and naturally when you see a container your first thought is, let's increase the size of the container. But the problem is with this approach is that by default at Google, the way we have our configuration set up is that if you increase the size of your container, it also increases the XMX by the same amount. And this is sort of not well understood by a lot of people who are Java developers because it's sort of unintuitive, but this is how it is. And so we notice that these job owners will increase the size of the container, the XMX increases by the same amount. And while this is a little bit better because it relieves some of the memory pressure, because again, G1 uses XMX greedily, we see that this still results in container So we have a lot of server owners who say, okay, well, oops, sorry. We see a lot of job owners who say, well, okay, increasing container memory worked a little bit, so let's just keep doing that every time. And so their new approach for a fix of a container is to increase container memory. And then now we have these servers that are just absolutely massive, wasting tons of resources. All right, so what is the solution to these problems? AHS, yay. Okay. But you might be first asking, what about the use container support flag? You've heard of that, maybe. But this really doesn't do what it sounds like it should do, which is it does tell us that, hey, this is the size of the container. Let's set XMX to some multiple of this size. But again, this is fixed at runtime, and it doesn't really inform the JVM that, like, hey, like this is actually what the state of the container is. It just says, here's the maximum size of the container. This is how much memory you can use. Okay, so now let's talk about what the goals are for this adaptable heap sizing project. What is it supposed to do? Well, one, we want to make it so that developers do not have to set the correct XMX. So, like I said, you still have to set an XMX, but you no longer have to worry about it being the right value. You can set it arbitrarily high, and it shouldn't affect how G1 performs. Next, we want to prevent container if at all possible. So we should understand, based on the size of the container and the usage in the container, that, hey, we have to stop expanding the heap. We're at risk of a container And third, like I mentioned before with the memory cycle of doom, we want to prevent excessive heap usage. So this is what AHS should accomplish. Okay, so what are some non-goals of AHS? Well, AHS is not meant to replace proper tuning and configuration. So if you are, say, a reliability engineer and you have a really good understanding of your server and what sort of the workload looks like, then you can probably tune the GC parameters to be more optimal than what AHS will give you. So that is sort of a tough thing to say, like, hey, this is a one-stop shop solution for everything versus someone who is an expert. But of course, AHS should work with the majority of jobs. Secondly, AHS will also not prevent if the container is just too small to begin with. If you're in a rock in a hard place, if the container is too small, you just can't do anything about that. And finally, AHS should work for many workloads and most workloads, and we've seen this in practice. But of course, there will always be some pathological cases which AHS may not be able to account for. Okay, so now let's talk a little bit about how AHS was implemented and sort of the design of the project. Okay, so high-level overview. As you can see, it's not actually too complicated. There's only a few boxes and a few arrows, so it can't be that hard, right? So the first one is the AHS worker thread, which I've highlighted in green here. So the AHS worker thread is a lightweight native thread written in C++, and it is a thread external to the JVM that we enable at runtime. And what this does is it periodically queries container RAM information as well as the JVM GC information and uses this to help the JVM react accordingly. And it does so via the introduction of two manageable flags, which we'll call proposed heap size and current max expansion size. Now, what is a manageable flag, you might ask? It is just a flag that can be changed dynamically at runtime. Most flags that we set cannot be changed once the JVM starts, but there's a handy feature called manageable flags, which allows you to change it whenever you want, and the JVM can read these new values. Okay, so what exactly is proposed heap size then? Well, fundamentally, the way AHS works is that we assign a target GC CPU overhead percentage. And again, more jargon, but what is GC CPU overhead percentage? Well, that is simply the time spent by the CPU running GC versus serving application threads. So we have some target that we set by default. I think right now it's 20, so we say 20% of the time your CPU should be running GC. The rest of the time it should be serving application threads. So what does proposed heap size do? Well, proposed heap size is a way to help achieve this target GC CPU overhead. And so if we see that the current GC CPU overhead is higher than the target, then proposed heap size is increased, and vice versa. If the current time spent doing GC is lower than our target, then we basically say, hey, we can shrink the heap. Intuitively, this works because the bigger the heap, the less amount of time we spend doing GC. This is kind of intuitive, but it works because obviously the larger the heap, the fewer times you have to run GC, as well as the fewer wasted promotions we have from promoting objects that will die soon, and so on. So that's kind of the intuitive reason why this works. And proposed heap size also takes into account other heuristics when making the decision for what value to set it. For example, the size of the container, or sorry, how full the container is, as well as other user configurable metrics. And keep in mind that this proposed heap size is actually a soft target. So we'll get into a little bit more into that later, but it will not be something that the JVM has to enforce, but is sort of a hint as to what size we should have for the heap. Okay, so just to summarize, if the GC is on fire, we say, all right, let's increase the size of the heap. Whereas if the GC is chilling, then we can say, all right, let's shrink the heap. Okay, so let's take a look at how this works via some more explicit number examples. And keep in mind, these numbers I've just made up on the spot, but they're supposed to help you visualize what's going on inside the AHS worker thread. So let's say our target GC CPU overhead is 20. This is fixed at runtime. It'll never change unless you change it at the new runtime later. But for now, it's 20. It'll stay 20 for the lifetime of the Java application. So let's say now that we observe that the actual GC CPU overhead is greater than that. Well, proposed heap size, if it works properly, should change the heap, and it might undershoot or overshoot in the beginning, but eventually we see that the heap size of the JVM changes such that we end up achieving our actual target GC CPU overhead, right? So it'll fluctuate, and we see this in the graphs, but it does tend to converge around some value eventually. Okay, so that's just the first graph that I showed was just the GC CPU overhead graph, but how does this actually work with the proposed heap size flag? So let's take a look, maybe a quick quiz with no reward. Okay, so the target is 20, and the actual GC CPU overhead is 30. So right now, the CPU overhead is higher than our target. Now let's say our actual heap size is 5 arbitrary units. Okay, so what will proposed heap size be? Will it be less than 5, greater than 5, or equal to 5? Yes. Correct, it will be greater. Yay. Okay, so again, these graphs kind of show what the pattern is. We spend some time looking for the right size, but eventually we converge towards, say, heap size, which gives us the target GC CPU overhead that we want. Again, these numbers are all made up, but I'll show you some real graphs in the future. Okay, so that's proposed heap size. Now, what is current max expansion size? Like, what is the point of this flag? Well, this one is preventing the heap from expanding too much. So again, I mentioned earlier that there is a container happens when various RAM consumers inside the container expand to the point where we have no more space left. And so this current max expansion size flag is responsible for making sure the JVM heap is not the reason why this occurs. And the value of this is roughly the container limit minus the container usage, aka the free space in the container. Obviously, you don't want to expand more than that, right? And the behavior when we hit this limit is the same as hitting the XMX. So basically, if you're running Java and then you run out of heap space, then you have to run GC, right? So this is the same thing. Instead, when we try to expand the heap past current max expansion size, we say, no, we have to run GC. Again, this takes into account other heuristics as well, similar to proposed heap size. But for the most part, it's pretty straightforward in how it's calculated. Like for example, one heuristic might be we want to save this % of the container as a buffer, just in case other processes fluctuate in usage. But in general, is roughly equal to the free space. And yeah, it's a hard limit, like I mentioned. Okay, so another quick graph, no quiz this time. A container limit is 10 arbitrary units, and let's say the container usage is fluctuating, but for the most part increasing. You'll see that the value of current max expansion size now has sort of an inversely proportional relationship. So again, roughly equivalent to the free space in the container, minus some buffer. Okay, so just to recap, since that was a lot, the AHS worker thread is responsible for taking both the information about the container as well as information about the GC and using that to set two manageable flags, which are called proposed heap size and current max expansion size. Okay, so now let's talk about how the AHS worker thread actually obtains this container information. Well, the container information is obtained by querying cgroup. And cgroup is fairly straightforward. It's a way to monitor resource usage inside containers in Linux. It's available by default. And the way we get the usage for memory is we read the memory.memswap.usage in bytes value. And for the memory limit, we parse there's a file called memory.stat as part of cgroup, and we read the hierarchical memory limit value. The point of this is not to put long words there, but it's really just to say it's really easy to get this information. All you have to do is call an API that's available on Linux systems. And this information gives us a snapshot of what the container looks like at any given point in time. So we have to query this and update the values periodically. So just again, looking at the memory model that we had in the first few slides, like the memory.stat hierarchical memory limit value corresponds to the total limit of memory usage of the container, so basically the whole box. And then the usage in bytes cgroup information contains basically the usage. And keep in mind that this is the actual usage. So let's say XMX is really large. Well, it doesn't care about the value of XMX. It just cares about the actual amount of RAM being used by the Java process. Okay, now let's go to obtaining GC information. So for that, we have to read from the hsperf data file. So what is hsperf data? If you've used JVM, you may know about this, but it is basically just a custom formatted binary file written to by the JVM. It's useful for monitoring and performance testing, and you can write hooks in your code that will write data to this file. And so we at Google, we have some patches that we've made to the JVM, which allows us to track GC time information, like for example, how much CPU time is spent on GC, etc. And well, we break it down into the various components, but if we sum this all up, then we get total GC CPU time. And so we use these patches to write the GC information to our hsperf data file. And then we can easily read this hsperf data file from the AHS worker thread. I say easy, but it's actually, because it's custom binary format, we had to write our own parser for this file. Maybe there exists one already that I was not aware of, but we had to do it for C++, and it was kind of a pain. But anyways, it works, and so we just read for that. Okay, so step 4, JVM changes. So once we have these two flags, how do we actually influence the behavior of the JVM based on the values of these flags? Okay, so proposed heap size is fairly straightforward. We query this whenever we attempt to expand or shrink the heap. So when we shrink the heap, which occurs at various points during the JVM GC cycle, so for example, during remark, during full or after full GCs, etc., or during expansions, which occur also frequently, in fact more frequently than shrinks, but it happens whenever an allocation fails, after young collections, or after humongous allocations. So basically, we take a look at every time a shrink or an expand happens, and we say, okay, let's actually try to shrink or expand to the value of proposed heap size. Yeah, that's pretty much it. And if we can't, then we can't. If the expansion is too large, or if the shrink request is much smaller, like if we want to shrink to a heap that we just cannot because there's not enough space to handle all the live objects, then we can't. But we try our best. Oh, yeah, I think I just talked about this. But TLDR, during heap resizes, we try to resize to this value. Okay. Current max expansion size. Okay, so this value is checked whenever we try to expand the heap. And if you look at what an expand API looks like. Basically, you pass in the amount of bytes you want to expand by. So when the expansion request contains an expand bytes that's larger than current max expansion size, we actually just say, nope, you're not going to expand by that much. We're going to try to expand by exactly current max expansion size. And this effectively helps it treat it like hitting the XMX limit. So, if we try to expand and the expansion size is not big enough to handle all the allocations we want, then, later on we go to the code path. We go through the code path that eventually ends up calling GC. Okay, cool. So we've sort of gone over all of the various implementation parts. So hopefully you have an idea of how all these parts work together. Okay, now let's explore some of the benefits we've seen at Google from enabling AHS on some of our servers. So just as a quick FYI, the way that our cluster is architectured here is called Borg. I think I'm allowed to say that. We have a job, let's say, and this job is split up into many tasks, right? We want to use our many hardware devices to make business more efficient. But these tasks are split up into different cells. So we have different cells running various tasks, but these are all part of a single job. And the reason why I'm explaining this now is because some of our graphs are broken down by cell, some of our graphs are broken down by task, and some of them are broken down by job. So just understanding this helps us understand the scale of some of our graphs. Okay, so first of all, what are the benefits of HS? Let's just reiterate. We have simplified tuning because no need to worry about setting the right value of XMX. We should see a decrease in container errors because of the way current max expansion size works. And then we should also see significant memory savings for poorly tuned jobs because now we are targeting a specific CPU overhead for GC. And that helps us in the case that jobs are configured with way too much memory. And we are able to accomplish this with no perceivable difference in latency, which is really cool. Okay, so for simplified tuning, this I can't really show a graph for, but if you look at the way Java developers have to configure their, configurations, a lot of times you have to worry about setting the XMX, you have to worry about setting the non-heap values. Basically, you have to try and understand how much RAM is being consumed by every part of the process, but that's obviously not easy. So here we remove the need to do that, and you can just set XMX to whatever you want. Okay, so decrease in container errors. Let's explore how we were able to accomplish this through a case study of Google Earth. Okay, cool. And I apologize for this graph. The two colors are pretty similar looking, but there's a green one and a blue one. Whoever designed that, I don't know why they're at Google. No, I'm just kidding. But we have the blue graph and the green graph, and these correspond to various cells for the server. And the cells are, we enabled AHS on the green cell at an earlier date. Let's see, August something. And we see actually after we enabled AHS that the amount of errors we see go from hundreds of container per hour to 0. And it's more noticeable once we enable it in the blue cell because then combined there's a net total of 0 errors. So that's awesome. We also see that the scale of this is huge. This is not just some tiny little server, but we actually have 20,000 or so live tasks at any given time, spread among 600 live jobs at a given moment. And this, in total is using around 90 terabytes of RAM. So this is a huge service. And according to the engineer that I've worked with to enable this across their Google Earth jobs, throughput, CPU use, etc., all appear unchanged. And we've been running this for months with no reported issues. But you don't have to take my word for it because we have another case study. Wait, okay, yes. That sort of highlights the memory savings that we've seen for the poorly tuned jobs. And this will provide more graphs to take a look at. Okay, so for memory savings, we'll explore HS in Google Meet. Okay, so first, let's look at the memory savings we achieved in a non-production environment. So I think here, this is for one task. We have AHS rolled out in various different, stages. But in the first stage, we have a memory reduction in via AHS of 20 gigs to around 16 when we rolled it out for a partial set of tasks. But then by the time we rolled it out for all the tasks, because we're looking, this is the average for all tasks. we see that it went from 20 gigs to around 8 gigs, 6 or 8 gigs. It's hard to see from this graph. But basically, huge memory savings, and this happens also not in just a non-production environment, but in production environments as well. So here we see that before enabling AHS, this server or this particular task used an average of 12 gigs. The average task used around 12 gigs, but then after enabling AHS, we reduced usage to pretty much 2 gigabytes. Which I'm gonna stand here close to my monitor so I can see better. Okay, and so this is an average per task. So here we have 12 gigs for one task, and averaged across all the tasks. But if we zoom out and look at for a particular cell, these are the types of memory savings we saw. So for example, for one of the cells, we had across all the tasks in that cell an average memory usage of around 640 or so gigabytes. And after turning on HS, we see that drastically drop to around 140 or so. And similarly, once we enabled it on cell 2, we saw similar drops in memory usage. And now zooming out one more time, now looking at the entirety of the job, there's two graphs here, or there's actually 3 lines, but basically we can treat the 2 bottom lines as the same because they're kind of the same thing. So the bottom line is the actual memory used by the job in total. So across all the tasks, across all the cells, this is the total amount of RAM used. And so we see that as we gradually start to roll out AHS from one task to all the tasks, we saw a huge memory reduction from 8 terabytes of RAM usage from 16 terabytes of RAM usage to 8 terabytes of RAM usage. But keep in mind that this is just the RAM usage of the tasks. You also need to set aside some amount of RAM for the container where the tasks are running in. So that's what the blue line represents. So initially we had around 48 terabytes of container RAM allocated for this particular server. And as we rolled it out, we're able to say, hey, actually we see that we're using a lot less memory. Thus we're able to reduce our container sizes as well. And this gave us realized around 24 terabytes of RAM, which is amazing. That's a lot of money. Okay, so you might be thinking, well, okay, at what cost, right? Like we have so much memory savings, but there has to be some cost, right? And yeah, there is. Well, we'll be spending more CPU time doing GC, and that's very much intended based on the way proposed heap size is designed. So here's some garbage collection metrics. If we look at how we enabled AHS across various cells, you'll see that in the first graph, I guess the first 4 graphs really, they show how much time, or how the pause times and pause frequencies increased when enabling AHS. But again, keep in mind that this is a very much intended effect. We are intentionally saying, hey, let's spend more time on GC, and thus we're enforcing that we're using less heap. And so the 5th graph, or I guess the middle bottom graph, shows the increase from our CPU overhead percentage from what was before 1% to something that hovers around 10%. And of course, it's a little noisy, but you can see that over the long term, it does tend to average out. And you might be thinking, well, actually, why is it not 20%, right? You said the default is 20. That's true, but sometimes you have a scenario where, there's just not much to GC. Like, this is kind of more optimal, right? Like, you can't force 20% of time of CPU to be spent on GC if there's nothing to GC. So we see here that this one fluctuates between 5 to 20%, but stays around 10. And the last graph indicates the total cores per Borg cell. So yes, we are using some more resources in the CPU area, but we see that the savings for RAM significantly outweigh those additional costs. So how does that affect throughput? Well, these are some graphs, basically queries per second per CPU, and then cost per query, like CPU, they're the inverse of that. But as you can see, before and after we enabled HS on 2 of the cells, so those are the 2 vertical lines, there's really no noticeable difference in throughput, which is cool. And then I guess the last metric that we care about is latency. Again, we see that before and after AHS is enabled, there's really no noticeable difference in latency at all. So these savings were really huge, and the people that enabled it on Meet were really excited and are now trying to get other people to use it. Okay, so looking forward, what's next on the plate for HS? Well, one important thing is, obviously, with the OpenJDK community, we want to share our findings and our contributions and see how we can make this more available to everyone outside of Google. So we did present this to the OpenJDK, and we noticed that there are some similarities to existing requests for enhancements. Notably, proposed heap size has a very similar sister RFE called use softmax heap size to guide GC heuristics. So you can see that sounds kind of similar because with proposed heap size, we are setting our proposed heap size, and then for this one, we are using another changing value to guide GC heuristics. Secondly, for current max expansion size, there's also another existing RFE called dynamic max memory limit. So again, this one is similar because as current max expansion size is preventing the JVM heap from expanding too much, dynamic max memory limit aims to accomplish a very similar task. And we believe that upstreaming HS to the OpenJDK, at least in its current form, while it might be tricky, it shouldn't be logistically too much of a Herculean task because the JVM changes themselves are fairly lightweight. So if, say, you don't set any flags in the JVM, like if you don't touch proposed heap size or current max expansion size, currently I could add AHS to the OpenJDK and it'll have no effect at all. And again, the HS worker thread, which does the bulk of the calculating of how we should set these flags, this is completely separate from the JVM. And the reason is because this is very implementation dependent, depending on what resources you have access to. For example, for us, we read the GC and container information via certain RPCs, but if you're running on a non-Linux or some other environment, you might not have that. So the HS worker thread is flexible and can be made to fit your needs, but this is separate from the JVM. So if AHS is available in the JVM, people could write their own AHS worker thread, or they could use the one that we have. So yeah, a few people actually came up to me earlier and they mentioned that they were participating in the thread with OpenJDK, so I'm really excited about that. Hopefully we can chat more later. But yes, we've got the ball rolling at least for this. Okay, so another extension that's sort of important is that we want to realize the RAM savings that we've created, right? Right now we have heuristics which can be used to automatically adjust the container limit, but this is a little tricky because let's say you don't have this available. So at Google we have a tool that basically looks at how much time or how much RAM is being used by your processes and then uses that to gradually adjust the container limit appropriately. But if you don't have such a thing, then you might have tons of RAM savings from enabling AHS, but then you're not actually returning any RAM back to your pool and saying that you can use this. So it's definitely helpful to have some way to turn lower heap usage into realized gains by automatically returning or adjusting the container sizes appropriately. So here's an example of this in practice. So before AHS is enabled, if you look at the bottom lines, this is the memory usage of a particular server. I don't remember what it's from, but it's from a real one. As you can see, it's using up to 1.5 to almost 2 terabytes of RAM, which is huge, right? And as you can see, the memory usage is very fluctuating. And again, this is kind of a symptom of G1 because basically we say for G1, hey, we have so much RAM, let's use it. So you can see it gets really big, then runs GC, and then gets big again, and so on. But because of that pattern, our tool that adjusts the container limit was not able to actually decrease the container limit. You can see that's a problem because one party is saying, hey, I'm going to use everything you can get, and then the other party is like, well, if you're using it all, I can't take any back. So we have that pattern. But then as soon as AHS is turned on, we see that the RAM usage becomes a lot more stable. And then because of that, this tool is able to say, okay, you're not actually using that much of the container anymore. So then we're able to turn the 1.5 terabytes into around 600 gigs. So that's 600 gigs of RAM savings that we can now put back in our RAM pool and use for other jobs. Another interesting idea is, as we mentioned before, the main tunable in AHS is the target GC CPU overhead. So like I said, we have the default of 20, but maybe that value of 20 is not appropriate for every server, right? If you have a server that has very low workload, then you don't want to force it to try and spend 20% of its time doing GC. So in that case, if the value that we set is too high, that could result in GC thrashing. Or if it's too low, then we still run the risk of having excessive heap usage. So maybe a cool project would be to work with various data points to intelligently determine what would be a good value for this target GC CPU overhead. So like again, 20 that we set was sort of arbitrary. This was based on our understanding of what we've seen in the field, but we have seen that 20 can be high in a lot of cases. So having some kind of way to do that automatically for us would be great. Oh, and a brain, because machine learning is cool, right? Okay. I guess some other things that we want to look into are to have AHS work with non-Linux environments. So again, AHS is currently restricted to a Linux system because of the way we use C groups. And another kind of cool project that would be related to this is intent-based configuration. So you might want to use AHS and then set basically, hey, like I want to optimize for throughput, or I want to optimize for very low RAM usage, or I want to optimize for very low CPU usage. Well, if you can, as a Java service owner, if you can say that in words rather than having to tune the various GC parameters, that would make life a lot easier, right? So I think AHS makes it easy to translate this mental model of, how do we want the job to perform and what do we want to optimize for into just setting that tunable flag. So I think this could help for that. And again, it's important to broaden rollout and adoption for AHS as much as possible. Obviously, you don't get any benefit from this if you don't use it. And it's still a challenging problem to take servers who have been running for years and introduce them, hey, we have a completely new way of doing GC. So I think broadening adoption, giving more information about how this works, and then telling them, hey, it should be safe to use, that process has been challenging, and I've learned a lot from that as well. So I think these are sort of, looking forward, the next things that we want to accomplish. All right, so a quick recap. How does AHS work? Well, it works by adjusting Java heap usage based on external information. Namely, it looks at the container's RAM usage and availability, as well as information about JVM GC. And it keeps this GC CPU overhead around its target value by adjusting the heap size accordingly. Hence the name Adaptable Heap Sizing. And we've seen the benefits here already, which is to reduce or eliminate container memory exceeded errors, save engineering time from having to manage the right XMX value, as well as significantly bring down the memory usage of a lot of these over-provisioned jobs. All right, so we have, I think, around, looks like 8 minutes left for any questions. So any questions from the audience? Oh, I don't know if I can even see if someone's raising their hand. Yes, up in the middle. Yes. So the question is, with AHS enabled, do we still have to set the container limits? And that's a very good question. I mentioned earlier that we have this tool that allows us to change the container limits accordingly. So for us at Google, the best case scenario is you enable AHS and you enable that tool as well. And that allows you to sort of come to the optimal heap usage conclusion. But for those that do not have that available, you do still have to be responsible for setting the proper container limit. So yeah, it does reduce tuning a little bit, but in that case, you still do have to have an idea of what is the general way it works. Now, I think that raises another useful point of AHS, which is if you set the wrong container limit, it'll be very obvious because the usage of the RAM, or you'll notice it via either the CPU time is spent too much or too little. So if you see a lot of thrashing, that means the CPU, the container limits are probably wrong. So I think the fact that they're able to work together, but also in the case you don't have that tool, it's still able to give you some useful information as to how to configure your service. Yes, in the yellow.
How will this work with very varying loads? Like we get process a file once every 3 hours, and the rest of the time we're doing nothing.
Mm.
How would this play in this when we're doing this?
Right. So the question is, how does this work with very variable workloads? For example, if you process a file once every 3 hours and the rest of the time you're doing nothing. That's also actually one of the best use cases for AHS because let's say in the case that we do have a very big spike in usage, AHS is able to, in those times, enforce more frequent GCs to try and keep RAM usage within the limits of the container. So basically, it gives us a safeguard against these spikes because we have this target, right? And it is actually fine for, okay, so I guess this goes a little bit into the heuristics of how it works. But basically, let's say the container is pretty much full. And during those spikes, we are in a period of time where we're very close to a container exceeded error. Then what AHS does is it looks at the fact that the container is almost full and says, okay, the current target of GC CPU overhead of 20 is not good. We increase that target. We basically enforce that we run more GCs during this time period, and then during periods of rest, we'll see that the heap usage again goes back down to what it was before. Does that answer? Okay. And of course, one more thing is that the current max expansion size flag again is the main safeguard there to prevent during those big spikes allocations from happening and enforce more GCs. Yep. Yes.
Current max expansion size, is that still capped by XMX?
Yes. So it will not. Yeah. I mean, if XMX is smaller than that, it'll just use that XMX value.
Yeah, so it means that most of your services have too big XMX.
Yes. Okay. Sorry, I forgot to repeat the question, but the question is current max expansion size capped by XMX? And the answer is yes. And for the second question, which was, that means that most of our services have too big of an XMX. Yes, that is also true. Because in the past, like I mentioned for the CMS situation, users were not punished for having too large of an XMX. However, they were punished for having too small of an XMX because their servers were not able to run. So we tend to see that in general, people set too large of an XMX. And so, yeah. Oh, yes.
Why not use JMX to get the GC information instead of parsing files dumped by the JVM?
The question is, why not use JMX? The answer to that is I am actually not familiar with JMX, so maybe that is actually a good way to do it. There's probably some reason though, but I don't know off the top of my head what that is.
Second JVM to query it.
Sorry?
You need a second JVM to query the values.
Oh, you need a sec.
You can easily read it from C++.
I see. Okay, so I guess for JMX you would need a second JVM to query it, whereas here, yeah, we just have a C++ thread that's able to query it. Okay, I have 3 minutes left. Let's see. Yes. The question is Graal VM. Yes.
Porting this feature to GraalVM?
The question is, are we porting this feature to Graal VM? So yeah, the answer for that right now is no. I guess the main priority we have right now is working on broadening adoption within Google as well as working with the upstream. I think if people are interested, I'm more than happy to work with people on Graal VM or whatnot to get this working there. But right now it's just me basically, and so there's not too much of a team to help me with that.
Are your users using ZenGC or Shenandoah GC?
The question is, are users using different types of GCs like Shenandoah? Right now, no. This is only for G1, but I think some of these principles do carry over pretty well for the other GCs. So we can also look as part of extensions to enabling this feature for other GCs. But right now, it's again not on the plate. So. Oh yes.
When can I use it?
The question is, when can you use it? That's a good question. Maybe my manager, John, who gave a talk earlier about the Java to Kotlin will have a better answer for that. But I think right now, again, it's pretty far out. Like right now, of course, we're still trying to get adoption within Google mostly. So that's sort of the next step after the OpenJDK. But maybe then we'll have something in a couple years. That would be really cool. Okay, 1 minute, so one last question. I'm sorry if anyone has questions in the back. I can't really see that far. So, Okay, I think that's actually it then. Of course, feel free to email me any other questions at my work email, or just come up to chat with me as well. I'm happy to talk for the rest of the day. Thank you.